Amy, how are you? Can you hear me?
Hello.
All good. How's your day starting?
Mine?
No, the Santa Claus's day.
I don't know anybody else on here yet. Um, it's going fine. I was reading through some of the doctor's paper just a minute ago, trying to do some definitions, and I saw an update to Clubhouse on my apps, and I was like, "Day right, update it this close to the event." And just as it started to go, beginning to download, I saw Katarina has started the room. I was praying that Clubhouse wouldn't have some kind of crazy glitch. How are you today?
Good, good. The same. Yeah, I'm excited about the talk today. I think it's a very important subject. Um, CO2 capture. You know, the heat wave in India. I don't know if you know about it, but it's been quite terrible. People are,
Yeah,
yeah.
yeah, I've
So,
heard some stuff about it. It's awful. I've written down a couple of questions. For me, it's going to be more clarification questions, right? Because it's like an important thing he's working on, but just it's one that's much more difficult to understand for you know, someone like myself, so a bunch of my questions are like, what's that?
that's fine. That's good. I think people in the audience will most likely have also questions like that. So I think that's good for clarification.
Yeah, and how's things with the over there at the moment? Are you all ready to go, ready to?
Yeah, the other, it didn't start yet, so that's good.
Ah, okay, cool, 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 cool.
Hi, Gilbert, come up. And
Hey, hi Gilbert.
hi, Taku Fumi. Welcome back. Nice to see you here again. I don't know if you want.
Well,
Our
welcome,
Hey,
guest
Katarina.
speaker. Hi,
Hey,
Gilbert.
Jamie.
welcome. Hi,
How's it going, guys?
hi. Well, thanks. Yourself.
Listening, Dr. Albin.
I didn't understand. I'm sorry.
Yeah, it's my phone acting up. I'm doing okay. Just a series of unfortunate events, but hopefully things will get worked out soon.
Oh, I'm sorry to hear that. I hope. I hope this
You have
gives you an hour of distraction.
Oh, definitely. I hope so too.
Science is always a good distraction when everything else is going crazy, at least for me. So,
it is. It's pure intellectual challenge, right? You can just focus on it, and progress is made. I always love this. This place always shows progress is being made. I mean, does anyone else find that really inspiring?
yes, very, and especially in this field. For me, it's not something that that's my work. So, I'm especially happy to hear. Yeah.
Yeah,
Mm, yeah.
I had to look up how to even pronounce some of the words that were in the doctor's paper.
Oh, that's good. That's good that you do that. I never do that. I just go ahead and yeah, I should do that too.
You're much more familiar with a lot of the terminology and stuff, though, aren't you?
With this, yeah, well, like the engineering material type of thing, I'm not too familiar with. But we will learn today. I mean, from the source.
Absolutely. I was boasting about the club to a friend last night, and I said to him, "You can't really get much more from the source than literally having the doctor with the paper to read. You just cannot. but that's it. And I said it's good that I'm not hearing it from any kind of headline where someone's like slanting it or half understanding it. I always love that.
Yeah. We'll start in a few minutes, everyone. Thank you for coming. We'll have Dr. Oh, he's on, but nobody. Can you see Dr.? He's there. He can hear us, but we don't see him.
One
That's
second.
so weird.
Yep, I see him. Oh no, I see the. Wait 1 second.
Gilbert, can you see Richard
I
Spontak?
don't see him. Is he on? Yeah.
I don't see.
That's so. Yeah,
Uh,
he maybe. Oh. Um. So I told him to restart the app and see if that works. We're starting any minute now when the technical issues are dealt with.
hopefully it's not that update.
Yeah. I don't know, is anything different? For me, I'm not sure. I always click through everything. I don't see anything.
Yeah, mine's updated, but nothing seems to have changed. So fingers crossed. It's just you would think these would be a kind of high, what do you call high
You're there.
priority bugs. Oh,
Hi. How are you, Rich? Thank you so much. It worked.
Can you hear me?
Yeah, but
feedback.
maybe we will all use that. Go. Let's try again.
Can you hear me?
Yeah, but there's this feedback noise, like I don't know if you can hear it, but are you using headphones today? Like, is there anything different than yesterday?
Okay,
It's still going on.
Yeah, it's given a lot of feedback, like it's like hearing you make the sound and reverberating that back on itself till it goes really kind of Doctor Who crazy.
can you hear me now?
It's still doing it. Do you have like is it coming through a speaker that's perhaps picking up your microphone to make it um echo in on itself? Because when you say, "Can you hear me?" It's like, "Can you hear me?" Kind of going silent like that. What is that called again? Is it just reverb?
Is it still on?
Yeah, it's still going on.
Yeah, it's still doing it. Yeah, you sounded like perfect. Yeah, yesterday. Is there something different?
Honestly, I have no idea why.
Yeah. So you're not using headphones, or
I'm not. I might
maybe
switch over to it.
do you have?
I'll switch over to headphones.
Yeah,
Anything
yeah.
urgent, like a hot topic, need to touch base.
For everybody else here, this is us. We're just ironing out a few technical difficulties, but we will be beginning very shortly. So thanks for bearing with us. As Katerina said, welcome to the Science Society.
Is this better?
Oh yes, so much
Much better.
better.
Yes, we can hear you clearly now.
Yes.
Thank you very
Perfect.
yeah, perfect.
Okay, let's
Okay,
start.
so it was the headphones.
Yeah,
Yeah.
apparently. Great, thank you. It works. So, yeah, welcome everyone to the Science Society. Special thanks to Dr. Rich Spontak. Um, he is our special guest speaker here today. We are very honored to having him. And let me tell you a little bit about him. He is a distinguished professor of chemical and biomolecular engineering and alumni distinguished graduate and undergraduate professor at North Carolina State University. He received his bachelor degree in chemical engineering with honors high distinction from Pennsylvania State University and was later awarded the PhD degree in chemical engineering from the University of California at Berkeley. He then pursued his postdoctoral research in materials science and metallurgy at the University of Cambridge, UK, and condensed matter physics at the Institute for Engineering Technology, Norway, before he joined corporate research division of the Procter and Gamble company. Then later he accepted a faculty position at North Carolina State University. And since that time, Spontak has published over 300 peer-reviewed journal papers and over 35 scholarly works as book chapters and invited monographs, and his work has been featured on 31 journal covers and cited over 14,000 times. He is active in a diverse range of disciplines. He's very multidisciplinary. His primary research interests relate to the phase, behavior, and morphology property development of nanostructure polymers, polymer nanocomposites and coatings, electron microscopy, and stimuli-responsive soft materials. He received many awards. He was an elected fellow of the American Physical Society and the Royal Society of Chemistry. He has been on advisory boards for more than 20 international journals and holds editorial positions on 3 of them. And he has been recognized as an outstanding scholar, alumnus, and alumni fellow by the Pennsylvania State University, and he received also awards at the North Carolina State University for Global Engagement Outstanding Teaching Academies, and he's a highly acclaimed educator and academic mentor, and also a very one that also takes the the student as a person into consideration and values the student. So I think that is very impressive. And welcome, Rich. And please, Jamie, go ahead with your question.
Okay, so first of all, thank you very much, Doctor, for joining us. We're actually all very excited for this, and your bio is exceptionally impressive, but this isn't good enough for the Science Society. We are so curious. We want to hear, as I put it, the origin story of what made you into a science superhero. So, if you care to bring us on some of that journey on what brought you to here and how you got there and what fascinated you, we would love to hear it. Please, the floor is yours.
Okay, so would you like me to talk? Oh, I'm getting so much feedback. Let me just take my headphones off. I'm assuming you can still hear me, right?
Yes, we can.
Okay, so I'm actually I can't hear myself right now because there's so much echo. But would you like me to give the origin story before talking about the paper, or do you want me to talk about the paper first?
Just if you give us your origins first, if you just tell us a bit about yourself and what got you into the science and your particular avenue trajectory to this point, that'd be
Sure,
great.
sure. So, um, first of all, I have to point to the fact that I think I knew that I was going into academe all the way back in my high school years. Um, It was I was the complete nerd who uh, was sought out by pretty much everyone in my class. So I often received questions from my classmates all the way up until the wee hours of the morning, 2, 3, 4 a.m., when people were panicking. And for some reason, I never felt annoyed by it. I always felt like it was my service to help others. And so I've maintained that general paradigm over my entire career. The interest in science slash engineering actually came as an interesting transition because while I was in high school, I really did love math. I loved chemistry. I loved physics. I loved the challenge. I loved being able to solve problems. But I was also quite a writer. And so I wound up winning state level, national level writing competitions. And I had a difficult choice to make. When I went to college, did I want to pursue a degree in engineering or a degree in journalism? And I often think back, if I went the journalism route, where would I be these days, and would I actually still be alive? But it turned out that over the years, I've been able to weld those two passions together in my pursuit of an academic position in a STEM field. So I chose chemical engineering because I was told it was the most difficult of all the technical fields at the time. And I basically had the attitude of, well, I'll take on the most challenging, and if I don't like it, all of my credits could transfer to other fields. And it turned out that I fell in love with some aspects of the field, and I use them quite frequently to this day. So for me, a lot of it is very much about high level problem solving, creative problem solving. um, I always tell my students to be resourceful. I think that's one of the most important characteristics of a good scientist, a good engineer, is to find a way. I never allow obstacles to keep us from reaching a goal. I always tell students if you hit an obstacle, you go around it, you go above it, you go under it, but you overcome it. And it has served me well personally and professionally over the years, um, and I consider myself a very very fortunate person to have found the ideal type of profession for me, where I could marry my love of science, my love of problem solving and engineering, and my love of writing. I get to do all of the above, and I just consider myself very very fortunate. So that's pretty much my origin story. It's not as impressive as being bitten by a radioactive spider, but it is what it is.
I would argue that this is more remarkable because this is actually real life. And listen, at the end of the day, everybody gets bit by a spider at some point, you know. Not everybody can actually mix multidiscipline science and problem solving into what you're going to talk to us today. So thank you very much for that. And so whenever you're ready, we will just love to hear you start your talk. Thank you very much.
Okay. Oh, very welcome. I'm glad to hear that you could relate to that origin story. Um, it's it comes from the heart, and it is what has been my driver over the years. So let me go ahead and get started then on discussing this paper. And again, I'm sorry if you want to interject at any point, feel free, but I'm wearing my headphones off my ears right now because there's such a tremendous echo that it would be, I wouldn't be able to talk. So, okay. So I'm going to first, before getting to the paper itself, let me set the stage, because the paper itself had to be condensed significantly from what it was. And so there were parts of it in terms of motivation that got lost in translation. And I wanted to cover those briefly to again put things in context. I always think that's very, very important for any scientific study. So, first of all, I think it goes without saying that there is a need to capture carbon from emissions. I mean that's a kind of a no-brainer these days. If you know about the Intergovernmental Panel on Climate Change, the IPCC, they're the ones who have been tracking the global temperature as a function of time over the past few decades. And they're the ones who basically have shown that there is an obvious increase in global temperature. And the date that they often ascribe as being critical, which is 2040, is simply a linear extrapolation of what the data are right now. And that linear extrapolation to 2040 gives us a temperature increase of about 1.5 degrees centigrade. That is a considerable change in temperature. But what's interesting is that while uh, climate change has captured the interest of many people, not unfortunately as many companies as we would like, but there are other reasons for capturing CO2 that kind of fly under the radar. So, for example, the most common way to produce hydrogen, and hydrogen is used in a wide variety of applications, not just as a fuel source, but it is used in a variety of different commodity and specialty chemical processes. It is used in the microelectronics industry. It is used in pharmaceuticals. And so the common way to produce hydrogen is through what's called the water gas shift reaction, which involves petrochemicals. And one of the problems with producing hydrogen this way is that it comes out as a mixture of hydrogen and CO2. And so, to really move economies towards a hydrogen rich economy or hydrogen driven economy, it becomes important to remove CO2. In addition, there is a commodity that we refer to as biogas, which is basically methane that is acquired from living organisms. And unfortunately, there is also a problem oftentimes with CO2 contaminating methane from that source or methane from fracking operations, where you might see CO2 being pumped into the earth to remove methane gas. So again, if you could extract out the CO2 from the methane, you actually improve the fuel efficiency of the gas that is mixed with it. Um, then, if we look at a very different um, set of circumstances or applications, one could think about well, something as exotic as extraterrestrial travel. The ISS, International Space Station, for example, has had to develop methods for scrubbing out CO2 from the atmosphere of these confined environments. That's going to become increasingly important as you start looking at longer trips or even colonies on, for example, the moon or Mars. But it's not restricted to extraterrestrial travel. One could also be looking at submarines and underwater marine travel. So, all of these instances are cases where CO2 has to be selectively removed. The last one is one that we don't commonly think of, but uh, you all recall from the COVID pandemic these pictures of people in hospitals on ventilators. Well, the tubing from those ventilators is intended to remove CO2 from exhalate, and so one could also imagine removing CO2 from biomedical for biomedical applications. So there are lots of different reasons by which we want to selectively remove CO2, um, and there are different ways in which it can be achieved. So the most common way for large applications like power emission plants or cement processes, which give off a lot of CO2, is to rely on aqueous amines. And this technique is called absorption. And the idea is that these chemicals, like the amines, have a very high CO2 solubility. And so, if one can then extract out the CO2 using these amines, then whatever other gases are present can be purified. The only problem with this is that there's a large footprint. If you've ever been to Texas and you've seen distillation plants and so forth for the petrochemical industry, the amine scrubbing plants aren't quite as big, but they still have a big footprint, and there's always the chance that amines, which are corrosive, toxic, and all that, can escape into the environment and have an effect on animal life and plant life nearby. Then there are inorganic membranes. So we're talking zeolites, we're talking um, metal organic frameworks where CO2 is adsorbed onto the surface. And this usually relies on size selection. So uh, these are commonly used, but they are expensive and they're incredibly fragile. And so there is a lot of interest in trying to come up with an alternative, which is where the organic membranes come in. The organic membranes, on the other hand, uh, can be modified to allow for size selectivity. Let big molecules get through uh, slower than smaller molecules, or they can be based on solubility selectivity, where you use thermodynamics and chemical affinity to try to get the CO2 to basically get pumped through the polymer faster. The advantages of organic membranes: they're typically mechanically robust, they can be highly tunable, and they can be scalable. And I should point out that they're less expensive than the inorganic membranes. So that's kind of where this all started, to kind of put things in perspective. And I've been working in this area since about 2000. Um, I had a paper back then in Science with colleagues who are now at UT Austin, whereby uh, we looked at frustrating polymer packing using nanoparticles. And it worked well. It has been adopted actually in the industry. Um, but in terms of CO2 removal, that has always been a challenge. And so we had introduced polyether membranes back in around 2001, 2002, uh, which really worked well and got a lot of visibility out of that, but it still was problematic. And I'm going to show you the reason why I say it was problematic, because there is what we call a performance plot that kind of guides all of this research into membranes for any kind of gas separation. Now, again, before getting to the paper per se, I wanted to point out the strategy. The strategy behind the paper that just appeared in Science was to marry or combine together two different mechanisms for transport. I'm going to preface that by pointing out that this idea of combinatorial engineering basically can be used in a lot of different ways. And I'm going to give you a quick example to show you how this can be used so that you can kind of get a feel for how we used it in the science paper. So here's an example. What if you chose two different components that had vastly opposite attributes? Could you somehow combine those in such a way that you would, in fact, get something that had a synergistic property? So here's the example. If you take nanocellulose, to be more precise, nanofibrillated cellulose, and you just make a film out of it. This is, a nice green material. It is widely available. It's sustainable and all that. But if you make a film out of it, it is a great barrier material. No gases get through it, and that's because much of that cellulose is crystalline. Okay, so we would say that this type of material is highly size selective, which means that it is affecting the diffusion of molecules through it. Whereas if we added to that humidified ionic liquid, now the humidified ionic liquid is just the opposite. It has a high affinity for CO2 in particular. It's hydrophilic, it's CO2 philic, and it is not diffusion selective, it's solubility selective. So basically, we can design from the ground up a material whereby we can put together these opposite attributes, and ultimately, what we find is a sweet spot. And that sweet spot is where we find that the selectivity of CO2, and this is typically relative to another gas like nitrogen, the selectivity goes through the roof. it becomes extremely high over a very, very small range of humidity levels, such that in between these nanofibrils of cellulose, we have ionic liquid with a little bit of water, and that is enough to give continuous pathways to the CO2, but nothing else. Nothing else goes through nearly as fast. And so selectivity is a term that I use to basically say it's the ratio of the permeability of CO2 to the permeability of another gas. And we choose nitrogen as our surrogate for air. Okay, so we wind up seeing that the uh, selectivity of CO2 to nitrogen is extremely high at over a certain range of relative humidities. And if we go too far with the amount of humidity that we add, then we see that the system opens up widely and everything can go through. The selectivity drops, but the permeability for CO2 goes also through the roof. So we have what is typically referred to in this area as a trade-off. If you want high selectivity, you typically work at low permeabilities. If you want high permeability, you typically work at low selectivities. This, this trade-off, also known as an upper bound, was first identified by Lloyd Robeson of Air Products, and it's an empirical observation. There isn't really a theory behind it, but it definitely uh, controls most of the performance metric in this field. So if we can somehow get above that trade-off line, with below which thousands of different types of membranes are located. Okay, it's really hard to get above that trade-off line. But if we can, then the performance is something that could be considered as a way to advance the field. Okay, so now let me go ahead and refer to figures in the paper. So if we look at figure 1A specifically, polymer membranes can be identified in different ways by how thick they are. The thicker they are, the more likely it is they will be self-standing. So they don't have to be supported on anything, and these tend to be on the thicker side. What has happened over the years is to cut back on the thickness, and that thickness really is where we run into a major resistance. Because imagine that we have to have molecules that are basically traversing through the membrane. So it has to find diffusive pathways. Okay, that is resistance. And so if we can make the polymer film thinner, then we can avoid some of that resistance. Well, we support the polymer membrane if it becomes so thin that it cannot stand on its own anymore. And the support is typically a highly porous polymer, something like cellulose acetate. But because it's so porous, we no longer have a diffusive barrier there. Now, what we did is quite a bit different. So we too had this thin polymer membrane sitting on top of a support. Okay, but we chemically modified the surface of that thin polymer layer so that now that the top, just the surface of that polymer layer, became highly hydrophilic and CO2 philic. The way that we did this was to grow polymer chains off the surface. And now we're looking at polymer chains that might be anywhere from 10 to 100 nanometers at most in thickness. But the purpose here is for that very, very thin nanoscale layer to concentrate CO2 from a mixture of gases. And so if you now look at B in figure 1, what we see is that we start off with a mixture that's primarily nitrogen with some CO2, and that uh, ratio is 90% nitrogen, 10% CO2, and it's humidified. The humidity is necessary to activate that surface layer. So it makes the amine groups more CO2 philic. And now that top layer concentrates the amount of CO2, and the polymer that is serving as the substrate, it is a naturally highly permeable CO2 polymer. And so basically, it's kind of like um, having a situation where you have all these different types of cars trying to enter into a freeway, and there is a special lane that only allows uh, cars of a certain color or a certain type to pass through without any problems. In fact, they just wave people through instead of having to pay a toll, and you wind up now getting these cars onto the freeway immediately so they can go zipping along, whereas all the other cars are stuck behind. They still have to pay tolls. Okay? So that's what we're trying to do here in principle. And the way that we do this is to combine two different mechanisms of transport. That very, very thin layer of polyamide that operates by a transport mechanism called facilitated transport. It is chemically augmented transport. So what happens is the CO2 will actually interact with the amide groups. It will, uh, in the presence of water, it will become ionic, and it will be able to transport faster through that thin layer than any of the other molecules. The water doesn't transport at all because the underlying polymer substrate is hydrophobic. So the water is stuck on the surface. The nitrogen will come through, but at a much, much slower rate. And now in that orange region, we have a different mechanism which is called solution diffusion. And in this case, the permeability depends on the solubility, which for CO2 it really isn't that high, but the diffusivity. And the diffusivity here in that orange region is extremely high for CO2. And that's what we take advantage of. So the top layer, the nanoscale layer in region 1, is intended to concentrate the CO2. It is not a separate polymer film. These are polymer chains that are grown onto the surface of the polymer substrate. And then the CO2 can quickly migrate through that orange region and the macroporous substrate. And so we see a vast increase in CO2 permeability relative to the nitrogen permeability. In figure 1C, the chemistry of that top layer is shown, where we show the hydrogen abstraction route, basically introducing an initiator on the surface and then growing polymer chains off those initiator sites, and then modifying those polymer chains to introduce amide groups, which are very important. And the spectra that you see in 1D Those are obtained from X-ray photoelectron spectroscopy and basically just confirm that yes, we are getting nitrogen onto the surface of both the PTFE-AF, that's basically amorphous Teflon. So this is a glassy material. It is not semicrystalline, but it is a highly fluorinated material. And the PDMS is polydimethylsiloxane, which is a rubbery material. And in both cases, we see that we do, in fact, get nitrogen on the surface. So if we migrate to figure 2, the takeaway message from these two sets of graphs, the CO2 permeabilities are shown in A and B as functions of pressure and temperature respectively, and then C and D show the CO2 to nitrogen selectivities. And what you see, this is really very important. If you look at the permeabilities in A and B, for both PDMS and the Teflon, the PTFE amorphous form, you'll notice that there's virtually no pressure dependence, which is to be expected for solution diffusion, and there's a slight temperature dependence, and it goes in opposite directions. So the materials actually have a different response to temperature. Okay, now what happens when we aminate the surface? The permeabilities of both of the membranes goes down, okay? In some cases by a little, in some cases a little bit more. But what you see is that's very important here is that the pressure dependence is non-trivial. And this is a signature feature of facilitated transport. It basically reflects the fact that you have only so many chemical carriers that can move the CO2 along. So if you go to high pressures, you'll see a reduction in CO2 permeability. And that's exactly what we see in figure 2A. In figure 2B, we see that same reduction in permeability, but now we see that as we increase temperature, we are in fact seeing different extents of increasing permeability. If we go to the selectivity, well, the most important thing to realize here is that initially the two parent polymers, the PDMS and Teflon, have actually very low CO2 to nitrogen selectivity. But as we aminate the surface, you see that we wind up increasing the level of selectivity significantly by orders of magnitude. And that's really the key. So, one of the important aspects of studying these types of materials is to look at what's actually happening at the surface. And so, if you look at the supplementary materials, we provide a lot of spectroscopic evidence to show that, yes, there are chemical changes to the surface. Yes, there is introduction of nitrogen, which is important. Okay, but picture can be worth 1,000 words. And so if you look at figure 3, we provide a number of different images of the surface. So the images in A through D all come from scanning electron microscopy. And really, you can't see a whole lot other than some evidence of de-wetting. But that's about it. If we look at the AFM images in E through H, what you see is both evidence of height images in E and G, and F and H are what are called amplitude maps to give you an idea of what the structure looks like. Now, this type of structure is very, very different from what you have of the unmodified materials. Those are the insets. And those indicate that there is no structure of these materials before they are modified. But once they're modified, they start to show kind of this de-wetting behavior. Now, the de-wetting behavior actually makes sense in hindsight because we were preparing these large samples using a UV source that was relatively small. And so if you look back at the chemistry in figure 1, you'll notice that for the first 2 steps, we need ultraviolet radiation to both introduce the initiator and then propagate the polymer chain. Well, if we don't have a uniform UV source, then there's a good chance that we're going to wind up seeing artifacts on the surface, such as de-wetting droplets, even at the nanoscale. So one way to get around that was to introduce a much larger UV source to try to avoid any gradients in terms of the polymerization. And what you see in the last 2 AFM images in I and J of figure 3 are results that indicate that most of this de-wetting behavior has been removed. So in I, that is a height image, and it very clearly shows that there are some features that protrude. And we were kind of curious about this. Now, the height image here is it's a relatively small height differential. So I believe it's only about 12 nanometers. And what you see here are these regions that are circled. The corresponding phase image. This gives you an indication of differences in modulus, or how stiff or how soft something is. So the softer something is, the darker it will appear in the phase image. And what you see is those regions that are circled in I, they're also circled in J, and they always appear dark, which indicates that these are in fact not individual polymer chains, but kind of groups of polymer chains, what we call patches, whereby these are now indicative of these chains that are introduced on the surface. And if you again go to the supplementary materials and you go to figure 12, S12, you'll see this in 3 dimensions so that you can get a better idea of how exactly the surface looks. And the one that I would draw your attention to would be the lower figure, because that shows the height differential at about uh, just under 12 nanometers. Okay, so what we see is that we have not only spectroscopic confirmation that we've modified the surfaces, but we have morphological or topological information as well. That's all very nice. It's nice science. It's nice to be able to do these types of analyses, to be able to confirm that we have what we think or what we thought we had, but the proof is in the pudding. And so now if you go to figure 4, this is the litmus test for polymer membranes. I referred to that Robeson tradeoff, or the upper bound, earlier. And so now you're going to see very specifically where the materials that we develop stand. Just as a precursor, let's turn our attention only to figure 4A. And in figure 4A, there are a couple of important things I'd like to point out to you. The first one, since we're looking at, again, selectivity on the y-axis, permeability on the x-axis. Permeability is often expressed in terms of Barer. In the paper, we do provide the conversion from Barer units to something that's more SI friendly. But you'll notice that it is on dual logarithmic uh, axes. And I will first draw your attention to the gray solid line. That is the accepted Robeson trade-off line. Okay, and almost, I probably would say somewhere around 90 to 95% of all polymer membranes lie below this line. Then, if we look at these red squares, those were introduced only a couple of years ago by another group that was trying to show that they could use polymers of intrinsic microporosity, otherwise known as PIMs, P-I-M, as indicated here. These types of materials are incredibly good because they can take CO2 and permeate it at very, very high levels. So you'll notice that we're looking at anywhere from 10,000 to 100,000 bar. That is extremely high. And we've previously worked with some materials that provide CO2 permeability of about 26,000 bar. That was polytrimethylsilyl propyne. Okay, and these are essentially nanoporous polymers. Okay, and they suggested that this upper bound should be moved, and so that's the red line. Okay, I divided this chart into quadrants. The first quadrant I call the Goldilocks quadrant because that is where we have ultra high selectivity and ultra high permeability. The only commercial materials that are put onto this graph are the ones shown in the circled area. And that gives you an indication of how many polymer membranes have actually gone into production. It's a small number. If you look at that idea that I showed you earlier with the nanocellulose and ionic liquid, that's up here. It's above the trade-off line, but it's also very low permeability. So that's problematic. There are a number of polymers shown by triangles, open triangles. Those show a lot of promise. Those often are block polymers that have a polyether segment, and they do work well. But if you look at where the unmodified PDMS and Teflon are located, they're in that low fourth quarter or fourth quadrant. By introducing the surface modification, we can increase the selectivity significantly. Well, in some cases, we do see a reduction in permeability. But if we change the temperature a little bit, we could potentially overcome that difference and again have everything wind up in the Goldilocks region. So the idea, once again, is to take ultra high permeable polymer membranes that are already used. These two polymers are used in a number of different separations. So there is no additional cost associated with using these materials. Once they are surface modified, their performance brings them up here well above the upper bound, the trade-off. Now, in all fairness, in figure 4b, we look at just the first two quadrants. And the reason we do this is because we wanted to compare our materials which marry facilitated transport with solution diffusion transport and see how they compare. And yeah, they compare very favorably, and only two of these facilitated transport membranes have been considered for commercial implementation. These types of materials are much more expensive to synthesize, and most of them are strictly for academic interest. They will never be used. So we wanted to not just do good science here, but we wanted to do good science that mattered. Because now that we have materials that are highly selective and highly permeable, we can have materials that could be put directly and immediately into use. The cost associated with the surface modification is going to be minor, and so there won't be a major uh, expense involved here. And more importantly, the membrane modules that were developed for the PDMS and the amorphous Teflon, they can still be used because our surface modification is only on the order of tens of nanometers in thickness. So there's no real change in dimensionality. So that was the whole point of this work. Um, it involved experts in membranes. It involved experts in polymer science. It involved experts in characterization, and it was a great opportunity to show how, if you bring all the pieces of the puzzle together in a new and creative way, one can basically develop a revolutionary approach. This idea that we introduced of marrying the two different um, types of transport, this is quite unique. Uh, no one has ever tried this before, and it really works well. Surprisingly well, I might add. I did not expect it to work quite this well. So that is pretty much the basis for the paper. And I would be very delighted. I'm sorry if I ran a little bit over, but I'm still hearing a little bit of an echo, which is why I'm being a little bit distracted here. But I hope that I've given you a flavor for not only the importance of coming up with polymer membranes, because we always have to have a rationale to do good science and do good engineering. It's never just as an academic exercise, and so we have a good reason. We really do want to try to mitigate the CO2 issue from you know from emissions that is affecting climate change, but also it can be used for fuel purification or oxygen purification where needed. So there are lots of different ways in which this can be used, and we wanted to find a way to do this, which really took the best of two different mechanisms and married them together. And we think we came up with a reasonably good synergistic result. So, with that, I will open the floor to any questions. And I'd like to thank Katerina especially for the invitation to join you this morning. Sorry if I ran a little bit over, but as you could tell, I'm just slightly passionate about this work, and I really wanted to share it with you.
Thank you so much. This was wonderful. Like, and even me could, follow and get excited and passionate about your work. So, you know, So I really
Well, it's
appreciate.
nice. It's nice to know that I can be contagious.
Yes.
Definitely.
Right,
Thank
that's
you
the
so
best
much.
compliment for a scientist. Yeah, thank you so much. So please go ahead with questions. And Jamie, yeah, sorry if I spoke over you.
Oh no, I was just showing my appreciation. So, who do we have up first, Katerina? Who do we have in the audience?
Yeah, please flash your mics. Whoever is here, Frank, Dr. Shah, Gilbert, Dennis, Rich, and anyone else in the audience, please raise your hand. And yeah, go ahead with your question. We have around 15 minutes.
Yep.
So thank you. Yeah, Rich, go ahead.
Yeah, I came in a little late, so apologize here. I hope I didn't miss something here if my question was already answered. But from what I could read, it seemed like it has this approach has a great opportunity for CO2 effectively concentration and um, purification from other, well, water or nitrogen. Are there ways to functionally make it uh, separable from, say, oxygen, and or are there ways to potentially to think about experiments that might be able to separate, say, O2 from CO2, or vice versa?
Oh, actually, hang on, I've got to take my headphones off again to avoid the echo. But the nice thing about this is that it will separate CO2 from a lot of other gases. So if you wanted to remove CO2 from oxygen, that would not be a problem because it turns out that the permeability of oxygen is almost the same as the permeability of nitrogen. And so the results that you see here for CO2 relative to nitrogen, to a first really good approximation, they are going to be very comparable to what you would have for CO2 to oxygen. So typically, you don't want to remove the oxygen from CO2. You want to do it the other way around because typically the CO2 is the minor component. That's the one we want to concentrate. And so, and if you look at the concentration of CO2 in just air, it's of course a much, much lower concentration than either nitrogen or oxygen. So that's where it would be beneficial. Um, we haven't looked at, we did in the paper, we actually did look at CO2 separation from methane. It's one of the figures in the supplemental material, but we didn't look at other types of gases that might be of interest, primarily because most of our interest was in looking at CO2 relative to air.
Oh, thank you.
Does that make sense?
Yeah. No, that's great. Yeah, I guess I always think about concentrating mechanisms in, say, plants or other systems like C4 plants, for example, or CO2 or
Mm,
cyanobacteria, where they concentrate CO2 using effectively, separate compartments for where CO2 then gets turned into carbonic acid or otherwise, such
hmm
that you get that selectivity. So it's interesting to kind of see, like, yeah, how can we mimic nature, or do different ways that nature hasn't figured out, perhaps with good materials and straightforward plan of bringing researchers together to work on this from different fields. So it's really awesome.
Well, thank you. And that's really an interesting idea. I didn't mention CO2, for example, for packaging. But that's also another area that's more closely related to, the plant scenario, because it has to be very, very carefully regulated for produce to survive long shipments, transoceanic shipment, for example. Um, so yes, it could actually be used in that regard as well as a way to control CO2. Um, and I have not actually considered the possibility of using this with regard to a greenhouse type situation. But you've just given me food for thought because one of my colleagues is quite interested in horticulture, and I'm going to have a long discussion with him now about how we might be able to implement this as a way to provide a source for CO2. So I thank you for that. It's a really interesting idea, and you know, we typically don't use this as a way to um, uh, capture CO2 for immediate use, but there's absolutely no reason why it couldn't be. So I thank you for that idea.
And if I can invite you to come on Friday, but it's at 9 p.m. EST, we will have a guest speaker talking about his recent published work on artificial photosynthesis to capture CO2. So maybe that
Ah,
would also be a great collaboration in the future. I'm not sure.
yes, thank you. I will definitely look into it.
Thank you so much. Yeah, please go ahead with the question. Thank you.
So thank you so much for a wonderful and informative, paper that you shared with us. My question from you is about, potential of your, work. If you want to just work with other agrochemicals, and specifically, I was wondering about the chromophores. Do you think that your project can be part of different project, which if you want to work with those kind of material or not?
Okay, I have to admit that I only caught a few words in there because of the echo effect I'm having. But I caught the part about a different project or a different area of research. Could you possibly state that again?
Yes, I was just wondering about the agrochemicals and the different kind of, I mean, we can say chromophores. That was specifically my main reason to see that is there any, capacity or potential for merge that or use another material such as the chromophores in a system or not. I'm just thinking about another project. That's why I'm asking you you think that your project have a capacity to be part of another project or or not?
So you want to use this kind of idea for chromophores? Did I
Yes,
catch that
yes,
correctly?
but in a different system. I was just wondering if we want to have a kind of both reaction beside each other in a different system. And that's why I asked that if we want to just switch the material from the ammonium to another kind of material, so it's going to work out or not.
Well, I mean, the physical process is general. So it's a matter of tailoring the surface so that it has the right chemical affinity. Um, but I'm not. Do you want the chromophores to actually migrate through polymer membrane? Is that what you're
Yes,
trying to do?
so that was part of the idea, but another part of the idea was, have a both reactions separately because I'm just thinking about the kind of chamber, and there's a different mechanism in a chamber, and I was just wondering to ask you, how do you think about that? It's a raw idea. I cannot give you all of the details.
Yeah. I think that there are ways in which you can control permeation. Um, if I don't know if you necessarily need to have this hybrid approach. The reason why we needed it for CO2 is because the solution diffusion mechanism by itself was insufficient to get us where we wanted to go. And so that's why we added the facilitated transport layer. However, in your case, I mean, it might be possible to get away with a single type of membrane that is designed specifically for your chromophore transport. I mean, if you want to, drop me an email, and I'll be happy to chat with you more about it. Um,
Sure.
you
The
know,
main
if
reason is because you have I mean, much more information than me in this field, and I was just wondering if we want to add another layer, for example, with a different material, and
hmm
specifically chromophone is gonna be possible because you talk about the permeability and selectivity, and we know that they are part of the work, and we should consider that. So yes, of course, I will check. I mean, I will send you an email and ask my
yeah,
question. Thank you.
please
If you
do.
have an email,
I want
the
to make
email is
sure that
supposed to be on paper, right?
yes, yes, my email address is on the paper, and I just want to make sure that I thoroughly and correctly understand what you're trying to achieve. And you know, if you'd like, I could also set up a Zoom meeting with you, or we could talk by phone. But I'm just having a hard time understanding right now with the echo that I have. So it's a little bit challenging. Even I'm
Doctor,
echoing.
I was going to ask Doctor to see if it works. If you tap on the mute when a question's being asked, if maybe you won't get feedback from your own mic. I don't know, just it might work, it might not work. When someone's asking a question, if you mute it, you might not get the feedback, but we can try it. If it doesn't work, it doesn't work. Okay, next question, please.
Jamie, I know you have a few questions. Why don't you go ahead and ask?
Oh, that would be great, actually. Okay, first of all, I was letting everybody else go first before I hogged the mic for a moment. But, Doctor, that was an incredible talk. Thank you so much. I'm going to be reading about this for days and days and days, just trying to unpack all of this. So, but that being said, a couple of clarifiers for the layman's over here. One of the questions I had was, what sorry, it's my screen reader. What is a high solubility mechanism, and what does it mean to enrich the concentration of CO2? Is that like you've got a chemical that's absorbing the CO2 inside it, or yeah?
Yeah, so I mean, that surface layer, basically, think of it as a sponge. And so what it does is it actually attracts the CO2 from whatever gaseous environment it's exposed to. And the CO2 actually reacts with the amide groups, and it forms carbonic acid, which you just heard about. And that ion will actually transfer quickly through that nanoscale layer. So it is effectively a sponge, and it does. I mean, the whole idea of using amides is very similar to what, or means rather, is actually very similar to what you heard me say at the beginning when I was talking about different methods for extracting CO2, and you heard me refer to amines, liquid amines, aqueous amines. Amines in general are extremely good at interacting with CO2. And so we just put it in polymer form rather than liquid form.
So it's a means to an end. Boom, boom.
Oh,
Thank you.
gosh. That was
Okay,
actually pretty good.
moving swiftly on before I get booted from the room. My next question was the hybrid integration membrane strategy. When it's mentioned that in the paper,
Mhm.
I was wondering, is that, I'm picturing it in my head, is that almost like you've taken like two different, say, types of, say, kitchen, paper or something, then and putting them on top of each other, or is that like weaving them together in some kind of net way, or what's that? Am I not understanding that properly?
Right. So typically what's done is if you have a polymer substrate, you will put down a coating. Okay. Coatings come in a lot of different flavors. The one that you probably know the best is simply paint or ink. And that's a coating. You put it down, and if you're careful, you could actually peel it off. Okay. That's not what we did. We did not want to do that. Instead, we wanted to create a hybrid material so it will have different parts operating differently. One part will operate by facilitated transport, one part will operate by solution diffusion. There's the hybrid part. Now, the integrated indicates that we can't take this apart. We cannot go in there and start plucking off these polymer chains that we've grown on the surface. So imagine that instead of having a chemical reaction in a beaker to produce a polymer, which is a very common thing to do, instead, what we're doing is we're actually seeding the surface of our polymer substrate with initiator sites, and those initiator sites allow us to grow polymer chains directly off the surface. That's why it's integrated, because even though it has two different components, you cannot take them apart. They are one material. Does that make sense?
Yes, actually, that does make a lot more sense now. Thank you very much. Okay, I've got another question. If anyone's got any, though, you can just speak up just now before I carry on with mine. Does anyone have anything? I don't want to be hogging the mic over here.
Yeah. I think we have 2 minutes left, so yeah, that's the last question. So yeah, please go ahead.
Yeah, if I may, thanks, Dr. Spontak. I joined a little bit late, and I'm trying to get more out of your great sharing, and really appreciate your, a very detailed explanation. I was just curious with the selectivity. I understand that you did a surface a modification with UV and grow a selective layer, and when I see the words that a 150-fold of increase. What does that I haven't read to the end of the paper, so I guess you probably explained somewhere that it's that increases comparing to with reference of what, and the
Mm-hmm.
selectivity is against nitrogen only, or some
Yes.
other.
No. So the primary reference is nitrogen in this paper. We in the supplementary material we do look at methane, but for the most part it's nitrogen, and that 150-fold increase is basically if you look at Figure 4. And you see where, for example, in Figure 4A, if you look at PTFE AF in the lower uh, right in the fourth quadrant and compare that to what we get upon surface modification, it is about 150 times. There are more than 2 orders of magnitude increase in the selectivity. So that's where that comes from.
I see. Yeah, thank you. And
Sure.
so Well, with this, I would assume that this there's with introducing this. Apparently, there's dilemma. I mean, the trade-off between selectivity and the permeability. That this your approach essentially is a big contribution to one way of getting around, right? So I would assume that you can in the similar design you can have a similar algorithm to for other uh, uh, target gas, I guess target.
Yes, you're absolutely right. So the idea that we've introduced here is even though we chose CO2 because of its importance in terms of climate change and in terms of fuel efficiency and all that, but this is kind of a general approach where we can now use this idea of taking membranes and modifying just the surfaces so that we can achieve, we can start to get synergistic relationships and improve some properties without sacrificing other properties. So you're absolutely right. This idea could be extended to other types of systems.
Great, yeah, amazing, yeah, thanks.
Thank you.
Okay, great. Thank you so much. I think we even took more of your time than you offered.
Well, that's quite all right. I thoroughly enjoyed it, and I'm sorry about the technical difficulty. I honestly don't know what happened, other than last night I was doing a test for an awards symposium, an awards talk I'm giving in a couple of weeks in Japan, and I introduced the headset for the first time, and I think that's the cause for this problem. I don't know why
Yeah.
it's happening, so I'm still kind of learning about how to use this effectively without the technical drama.
Oh, yeah, don't worry about it. I bought last month or so because I wanted to avoid to have background noise when I'm in the lab, and it did the opposite. I bought expensive noise canceling headphones, and nobody could hear me anymore. Everyone told me it's horrible. We can't hear you. You sound like you're in a tiny tin box. It's very far
Oh
away.
no.
Oh, that was frustrating. So I get it. I don't know why sometimes more tech adds more problems, but that keeps us having problems to solve. So we will not.
Absolutely. Yep,
Exactly.
absolutely.
Thanks
So
Well,
for
it was a
bearing with
real
us, though, despite the difficulties. Thank you so much.
yeah.
it has been my absolute pleasure. And
And we're
I'm
going to ask you. Oh, sorry. Please go. Please go.
no, I was just going to say that this was a wonderful experience for me, and I hope that people who are listening find this useful.
Yeah, very. And I already know that your next talk will be even more exciting. And it's actually
Yes.
already being used. So, yeah, we are excited to having you back. And thank you, everyone in the audience, for
100%.
coming, asking questions. And yeah, follow the club. Um, Rich will
And
be
if
back.
anybody And if anybody wants to follow up with email, please, by all means. I'm always happy to explain what we've done and entertain new ideas. And if there's anything I can do to help you with your research, I'm delighted to do so.
You're wonderful. Great. It was
Thank you
an
so
honor.
much.
Yeah,
So
thank you
much.
very much, Dr. Spontak.
Bye,
My
everyone.
pleasure.
Thank you.
Okay, take
Take
care.
take
Thank
care,
you.
Bye.
Bye
Bye.
bye.
everybody.
Hi
Bye
everyone.
bye.
3, 2, 1. Bye.
Bye.